All right, welcome to Lecture 4 of CS 182. Today, we're going to talk about optimization algorithms, and we'll go into it in quite a bit more depth than we did when we first discussed gradient descent for logistic regression in Lecture 2. So first, let's start with a recap of gradient descent. So we have our loss function. We learned in Lecture 2 that a good loss function to use would be the negative log likelihood, which is what I have written out here, but in general, you could use any loss function you want. And we're going to use the letter L to denote the loss function, and it's a function of our parameters theta. And let's say that theta is two-dimensional, so we're trying to learn two numbers. We could visualize our loss function like this. So we could visualize this as a graph where the two horizontal axes are the two dimensions of theta, and the vertical axis is the loss. So you can imagine this picture basically represents the loss landscape. It represents the function L of theta. And if we start off at some point in this plot, at some value of theta 1 and theta 2, represented by the black circle here, one of the ways that we could find the best setting of theta 1 and theta 2, the one that minimizes L of theta, is by figuring out a direction that we can move, represented by this arrow, that would decrease L of theta. So we can figure out a direction that points towards that minimum point on the graph, and we move in that direction, then we will improve our value and hopefully eventually converge to the best possible value. So moving in a particular direction simply means finding the direction where L theta decreases, and then setting theta to be the old theta plus v multiplied by some small constant alpha. And this small constant is referred to as a learning rate or step size. Intuitively, it represents how quickly you're going to move in the direction v. You don't want to move too quickly because if you use a very large alpha, you will actually overshoot the minimum point and you'll come out the other side. Right? So imagine that arrow that I have in the picture. If that arrow were to be made 10 times longer, it would actually go down to the bottom and then all the way back up the other side and probably land at a location with a higher value of L theta than where it started. So you want to use a small constant. All right, so how do we select which direction to go? Well, it's perhaps easiest to get some intuition for this in one dimension. So imagine that theta is one-dimensional, and this is our graph. If we're located at this particular point, we could calculate the slope of the graph, and if the slope is negative, then we go to the right. If the slope is positive, then we go to the left, right? And that will bring us closer to the minimum. In general, if we have a multivariate function, then we simply use this procedure for each dimension separately. How do we know the slope? Well, to find the slope, all we have to do is calculate the derivative. So in higher dimensions, what we can do is for each dimension, go in the direction opposite the slope along that dimension, and the slope is obtained via the derivative, the partial derivative for that dimension. So v1 would be set to the negative of the partial derivative of L with respect to theta 1, and v2 would be set to the negative of the partial derivative of L with respect to theta 2, and so forth. Now, in general, we could take all of these partial derivatives and stack them up in a vector. So we can construct a vector where the first entry is dl d theta 1, the second entry is dl d theta 2, etc. And this vector is called the gradient. So the gradient is just the term used to refer to a vector consisting of partial derivatives with respect to each of the dimensions of theta. And the dimensionality of this vector is the same as the dimensionality of theta. All right, so well, and of course, in case it's not obvious, all you do is you set v to be the negative of the gradient. Now, in today's lecture, we'll discuss at length situations in which gradient descent works, situations in which it works poorly, and how we can improve it. And we're going to see lots and lots of pictures of gradient descent being visualized. One type of picture that we'll see a lot is a contour plot. So in this contour plot, the lines correspond to level set contours. So for all theta values along one of these contours, L of theta takes on the same value. This is much like an elevation map on a map. So if you imagine looking at a map of some mountains, you'll see these contour lines, and those contour lines represent lines of equal elevation. In the same way, in these plots of gradient descent, the lines correspond to lines of equal value of L theta. And we'll visualize the optimization path for gradient descent with lines. So each endpoint of each line segment represents a value of theta on one of the iterates of gradient descent. And the line segment between those points represents the step. And the step, of course, is the gradient direction multiplied by the learning rate, alpha. Okay, so this is a visualization of gradient descent, and we'll see lots of visualizations like this. Let's look at a demo of gradient descent in action. So here, looking at this picture, we can tell that this is optimization of a function with two parameters, so theta 1 and theta 2. And here the big circle, the big orange circle represents the starting point, and the smaller circle represents the ending point. Now, looking at this function, you can tell it's not a particularly easy function. It has these kind of narrow valleys. So if you were to imagine this was a topographic map, a landscape, it would probably be kind of a ravine, a long, slender ravine. This is a difficult thing to optimize. So what I'm going to do here is I'm going to move the starting point. And as I move the starting point around, you can see that the steps of gradient descent, they're calculated very quickly. So that's why it shows up instantly. The steps of gradient descent move down the valley, and then they gradually move along the valley. As I increase the step size, you can see they'll get further along the valley, but as the step size gets too big, then when you get to the bottom of the valley, you actually run up the slope on the other side, and you end up oscillating, right? So you go to the bottom of the valley, you overshoot, come up the other end, and then go back down the other side. All right, so we see from this visualization that there are a number of challenges that crop up when we're doing gradient descent. We have this oscillation problem where we go up the other side. We also seem to have a problem where we don't get all the way to the optimum. So as we're traveling down this valley, we get slower and slower and slower and slower, and we don't actually reach the exact minimum point. So what's going on here? Well, first, gradient descent doesn't always move in the direction of the optimum. Gradient descent will always take the steepest descent direction, but the steepest descent direction is not actually the one that goes directly towards the minimum point. And you can see in this picture that the first step we take from the starting point is actually moving away from the optimum, right? It's moving down the valley, but that move down the valley actually takes it further from the optimum. In general, gradient descent doesn't always pick the direction that is best. It picks the direction that is steepest. So imagine this kind of function. Again, this is a contour plot. So each circle or each ellipse represents points with an equal value of L theta. So you can imagine this kind of an elliptical pit. And the optimum is here in the middle. And let's say we start over here. Now the direction of steepest descent is always perpendicular to the tangent to the level set. So if in a picture like this you want to figure out what's the direction of steepest descent, just draw a line that is tangent to the contour, and the arrow orthogonal to that line will be the steepest descent direction. So this is the derivative, this is the gradient. And if we go in that direction, we'll kind of end up going down the valley and maybe a little bit out the other side. And at that point, if we compute the steepest descent direction, we'll go the other way. And then the steepest direction will go the other way, and so on and so on. And that's exactly what we see in the demo. Now, given infinite gradient steps, eventually this will reach the optimum, but it might take quite a long time. So the steepest direction is not always the best. Now we could wonder, is there a way to actually calculate the direction that is better? Is there a way to calculate a direction that goes towards the optimum instead of just the direction of steepest descent? We'll come back to this point later. There are actually ways to calculate better directions. But first, let's better understand the challenges that come up in gradient descent. So the loss surface that I drew before, the loss surface when we discussed logistic regression, is a very nice loss surface. Now, what does it mean for a loss surface to be very nice? Well, nice basically means that gradient descent will do very well with this loss surface. Why is that? Well, there are a number of things about this loss surface that make it nice. One is that it doesn't have narrow, steep valleys. So from any point, if you take the steepest descent direction, it'll kind of point towards the optimum. Kind of all roads lead to Rome in this lost landscape, which was not the case for the lost landscape in the bottom left. Now, is our loss function actually nice if we're doing machine learning? Is our loss function really nice if we're doing logistic regression? So logistic regression, which is what we covered in lecture 2, that's a way of doing classification where the probability of a class is given by the softmax of a linear function of the input. So the parameters theta show up in the exponent, in the numerator, and the denominator. This is the equation for the probability of in logistic regression, and we take the log of that probability, and that becomes our negative log likelihood loss. The negative log likelihood loss for logistic regression is guaranteed to be what is called a convex function. Now, convex functions are often nice. This is not an obvious or trivial statement. So if you've studied convex optimization, you might be asking yourself, well, is it obvious why logistic regression is convex? It's not obvious, but it is possible to show that. It's quite involved, and I'm not going to prove that in this lecture. But let me explain to you what convexity means and why convex functions tend to optimize pretty well. So here's a function in one dimension. A function is convex if a line segment between any 2 points on that function lies entirely above the graph. Meaning I take any 2 points, I draw a line between them, that line will be entirely above the graph. It will not intersect the graph. In contrast, this function is not convex. For this function, if I draw a line between the 2 points, it will actually intersect the graph. It won't intersect the graph for every pair of points, but there exists a pair of points for which it will. Now, this function also happens to have 2 optima. It has 2 troughs where each one contains a local optimum. In general, a function can be non-convex even if it has only 1 optimum. So this function has a kind of plateau. It only has 1 optimum, but because of that plateau, if I draw a line between these 2 points, it will actually intersect the graph. So a function being convex implies that it has only 1 optimum, but a function being non-convex does not imply that it has more than 1 optimum. Convex functions are nice in the sense that simple algorithms like gradient descent have strong guarantees for convex functions. It's possible to prove that gradient descent on convex functions will find the global optimum in a number of iterations that is not too large, in a number of iterations that is polynomial. This doesn't mean that gradient descent actually works well for all convex functions. For example, the function in the lower left-hand corner of the slide is also convex, but as we saw before, for that function, gradient descent will take a very indirect path to the optimum. Okay, but convex functions generally are kind of one of the better things we could hope for. Now, what about the loss surface of a neural network? So logistic regression is a relatively simple algorithm. We'll learn more about neural networks in subsequent lectures, but for the purpose of today's lecture, a neural network is a more complex function. It's a function with many parameters, many layers of representation, and where we don't just have a linear operation on x followed by a softmax, we have a more complex mathematical operation. The precise definition of those operations will be defined in a later lecture. It's pretty hard to visualize the loss surface of a neural network because neural networks have a very large number of parameters. So you can't really make a meaningful neural network with just 2 parameters, therefore it's very hard to draw the loss surface of a neural network. But we can give it a try. So there's this paper by Lee et al. Called Visualizing the Loss Landscape of Neural Nets, which uses some clever dimensionality reduction tricks to try to roughly visualize the loss landscape of neural networks. It can't be visualized exactly because it is a much higher dimensional object, but with a little bit of clever dimensionality reduction, we can produce something that looks, a little bit realistic, that at least gives us some intuition for what's going on. And the picture that Lee et al. Came up with for a ResNet model without skip connections on ImageNet was this picture. Now compare this picture to the nice loss landscape that I had on the previous slide. This thing looks quite a bit worse. So there's your global optimum, and yeah, it's kind of bad. So you've got all these local optima. If this was a kind of a medieval map, it would say, here be dragons, right? And these are very dangerous places where you can get stuck. There's lots of big flat plateaus where you might go really quickly, really slowly. It's very non-convex, lots of local optima, lots of complicated features. Now, some networks are better. This is a ResNet model with skip connections. We'll discuss what skip connections are later. This looks like a much better loss landscape. It's still not great. It still has a lot of flat regions, but at least it doesn't have quite as many kind of crags and crannies and nasty places to get stuck. Okay, so neural network loss landscapes are definitely not convex. What are some geographical features in a loss landscape that we should worry about? There are three features I want to tell you about that are important to know about. One is the local optimum, another is the plateau, and the third is something called the saddle point. These three features, interestingly, I listed them kind of in order of how well known they are. Like many people know about local optimum, fewer people know about saddle points. And also, oddly enough, in the order of how bad they are. So even though local optima are the most obvious issue, it's actually one of the least bad. And even though the saddle points are one of the least obvious, they're also one of the worst things to deal with. But let's talk about what these features are. So local optima. This is something that many of you might already know about. It's one of the most obvious issues with non-convex loss landscapes, which is that you might have more than one point where the derivative is zero. So at any of these local optima, the derivative will be zero, which means that there's no improvement direction. Any way you go locally around that point will only increase your loss value. So the global minimum is also a local minimum, right? So at the global minimum, any step will increase your loss value, but that's okay because you're at the best value you could be. But this local optimum on the left in this graph also has this property where any local step will only increase your loss value. The derivatives are all zero, which means the gradients are zero, and you can't figure out an improvement direction. So this is one of the big reasons people used to worry about neural networks. It's widely known that neural networks have non-convex loss landscapes, and therefore they must have local optima, and that is cause for a lot of concern. Local optima are very scary in principle because gradient descent could converge to a solution that is arbitrarily worse than the global optimum, and you'd have no way of knowing, right? When you look at the derivatives, you just can't tell that this is not the global optimum. If the derivatives are all zero, and you're sitting at the bottom of a ravine where any step is going to only increase your loss, you don't know if that's the best point, or the second best point, or the 100th best point. It could be arbitrarily worse than the global optimum. A bit surprisingly, local optima actually become much less of an issue for very large neural networks. This is a question that has been studied quite a bit empirically and also theoretically. This is surprising. This was not an obvious thing to a lot of people for a long time. Neural networks with many parameters definitely have local optima in their loss landscapes for pretty much any reasonable loss. Surprisingly, these local optima are often good, meaning that there don't seem to be very many local optima where the loss is much, much worse than the global optima. This is, not an obvious thing. This is actually somewhat surprising. So here's a plot from the paper, The Loss Surface of Multilayer Networks by Choromanska et al. And let me explain what this plot is showing. On the horizontal axis, we have the loss value, the numerical value of the loss, this is a negative log likelihood loss, for the solution discovered by gradient descent. This is a histogram. So the vertical axis represents how many runs of gradient descent, each starting from a different random location, achieved that loss. So it's kind of plotting the frequency of runs that got that loss. And the different colors represent networks of different sizes. So larger numbers here correspond to bigger networks with more parameters. roughly speaking, these numbers basically directly scale the number of parameters in the optimization. And what you can see is that for the smallest networks, shown in yellow, there's a wide distribution of different loss values. It's still not that wide. All the numbers are between 0.08 and 0.10, so it's kind of a fairly small range. But there's some variability, which means that the optimization is falling into local optima with a range of different loss values. But as the networks get bigger and bigger, the frequency of networks that achieve different losses becomes much tighter. So for the red, the largest networks, you can see that there's still some variability in the loss, but the solutions are clustered much more densely, kind of in the range of 0.072 and 0.078 roughly, right? So the range of different local optima you get is much lower. And you could imagine this trend continuing further and further as the networks get bigger and bigger. The range of loss values gets narrower and narrower. What that means is that they do have local optima, but those local optima are all fairly similar to each other. They're all actually pretty good. There are no really, really terrible local optima, or if there are, they seem to be very rare. Now this is an empirical observation, and this is from some older work. Since then, there's also been quite a bit of theoretical analysis, and at this point there's pretty strong evidence that local optima for large neural networks are just not that bad. It's quite surprising. Okay, plateaus. This one is a lot less obvious. We could imagine a loss landscape where it's not that we have a local optimum, but we have a large region where the gradient of the loss is very small. And we kind of see something like this at the bottom of the ravine in the demo before, right? So the sides of the ravine have very sharp gradients, but when you get to the bottom, you have a fairly small gradient that gets you to follow along the ravine. So plateaus are actually very common in neural net loss landscapes, and you can't just choose tiny learning rates to prevent this oscillation at the bottom of the valley, because if you choose a tiny learning rate, it'll take you forever to get through the plateau. This is actually a really big problem, because if it wasn't for these plateaus, we could just use small learning rates and we would make slow and steady progress towards the optimum. But when these plateaus are really flat, a small learning rate might mean that it essentially takes you forever to get through the plateau. So you need learning rates that are large enough not to get stuck in a plateau like this. Later on, we'll learn about something called momentum, which really helps with this kind of problem. All right, so that's plateaus. Lastly, let's talk about saddle points. Saddle points are something that doesn't really exist for one-dimensional functions, but for functions in higher dimensions, saddle points are actually fairly common. So a saddle point is a point that is, you can kind of think of it as a local minimum along some dimensions, but a local maximum along other dimensions. At a saddle point, the partial derivative with respect to each dimension of the function is 0. But the function is increasing in some of the dimensions and decreasing in other dimensions. So a visualization of a saddle point of a 2D function is shown on the left. In the middle, I'm showing a quiver plot that represents the gradient vectors for that saddle point. So they're a little bit hard to see because they're small, but if you look at the little blue arrows, when you're far from the saddle point, the blue arrows do the right thing. They sort of, what you want to do here is you want to go either to the left or to the right, because the function increases there. So the function, decreases. So the function decreases left and right, and it increases up and down. So the blue arrows, when you're far from the saddle point, they kind of curve to the left or curve to the right, which is exactly what we want to see. But as you get closer to the saddle point, the gradients vanish. They become really, really small. Which means that even though you will eventually go off the sides and you'll properly optimize the function, when you're close to the saddle point, you're taking these really tiny steps. It's like a really bad plateau. So the green lines here on the right plot show the gradient flow. They show the trajectories that you'll follow for gradient descent. And gradient descent starts going really slowly as it gets closer to the saddle point. Now, you might think at this point that this is kind of an esoteric issue, like, well, what are the chances that you'll land at a point where the gradient, where the function decreases or increases in some directions and decreases in other directions? It seems very unlikely, very kind of random. So the gradient is very small in the middle. It takes a long time to get out of saddle points. Does it really happen that often? Well, in fact, yes. And this is where our intuition about functions from thinking about low dimensions, thinking about 1 or 2 dimensions, is actually very misleading. In 2 dimensions, a saddle point like this seems very esoteric. It seems very unlikely and very specific. But in fact, most critical points in neural net loss landscapes are saddle points. And this is because in higher dimensions, things just don't work the same way that they work in lower dimensions. So let's talk about this a little more. First, what's a critical point? A critical point is any point where the gradient is zero, meaning that all partial derivatives of L with respect to every dimension of theta are zero. Now there are different types of critical points. So critical points are points where the derivative is zero. But you could then ask, for a given critical point, is it a maximum, minimum, or saddle? Well, the way that you know is by looking at the second derivatives. So in one dimension, if you are at a critical point and the second derivative is positive, that means the graph is sloping upwards, that means you're at a local minimum. Right? So if you're at the bottom of a local minimum, the derivative is zero, the first derivative, but the second derivative is positive because you're going to arc upwards as you go to the right. If the second derivative is negative, then that means that you're at a local maximum. The graph is going to arc downwards as you go to the right. But in higher dimensions, you could have some second derivatives be positive and some be negative. In general, we can construct a matrix called the Hessian matrix. The Hessian matrix is basically the second derivative equivalent of the gradient. So the gradient is a vector where every entry is the partial derivative with respect to the corresponding dimension of theta. The Hessian is a matrix where every entry is the second derivative with respect to 2 entries in theta. So the entry 1, 1 is the second derivative with respect to theta 1 and theta 1. The entry 1, 2 is the partial derivative with respect to theta 1 and theta 2. Okay? So it's just a matrix of second derivatives. The Hessian matrix at a saddle point is going to have diagonal entries that are 1 for some dimensions and -1 for others. So for example, for this really nice function, the Hessian matrix might be 1, 0, 0, -1. So that means that you have a second derivative that is 1, that is positive along one of the dimensions, and a second derivative that is negative along the other dimension. Now, it doesn't have to actually be diagonal, it doesn't actually have to have zeros on the off-diagonal entries, and the entries don't have to be 1. This is just an example. Okay. Now, this is only a maximum or minimum if all of the diagonal entries are positive or negative. Or in general, for non-diagonal Hessian matrices, you would want it to be positive definite or negative definite. If you don't know what positive definite and negative definite mean, don't worry about it. You can kind of think about diagonal Hessian matrices for now. This is just to build some intuition. Now, imagine what happens in higher dimensions. In higher dimensions, you have many entries in the Hessian. So it's not 2 by 2, it's maybe like 1,000 by 1,000. And you have 1,000 different entries on the diagonal. How often is it going to be the case that all of those entries have the same sign? Right? So for a 2D function, well, having them both be 1 or both be -1 seems pretty likely. In fact, it's just as likely to be a maximum or minimum as it is to be a saddle point if the entries are just random. But in higher dimensions, it seems pretty unlikely that every single diagonal entry will be positive or every single diagonal entry will be negative. So most critical points in higher dimensions are actually saddle points. And that's actually kind of surprising if you think about the intuition you get from 2D functions. But in higher dimensions, it's just pretty unlikely to have the same sign for all the entries. So that's why in higher dimensions, most points where the gradient is 0 are actually saddle points. All right, so let's talk about which direction we should move when we're optimizing a function. So before we talked about steepest descent, which is what gradient descent does, but we somehow need our improvement direction in these complicated neural net loss landscapes to take us around all the dragons and all the monsters, all the local optima and all the plateaus, and wiggle our way right to the optimum. How can we do that? Well, Remember, we don't always move towards the optimum if we choose the direction of steepest descent. And we get all sorts of problems due to oscillations in these valleys, due to plateaus, due to saddle points. So what we'd like is, instead of wiggling back and forth like this, we'd like to find maybe a better direction, one that is more directly headed towards the optimum. So that's what we'll talk about in the next part.